The existing recursive coherent coherence attribute mapping framework, known as RCAM-He, works precisely for hydrogen. But when we scale up to helium, element Z equals 2, the math hits a wall. The current mathematical framework assumes that combining two recursive partners always produces a single, perfectly symmetric scalar value. This assumption holds mathematically if the system only produces a singlet state, where the total spin equals 0. But it completely ignores the quantum reality of the triplet state, where the total spin equals 1. In Z equals 2 systems, combining spin 1/2 entities yields a singlet 0 state and a triplet 1 state. The singlet channel is antisymmetric. Partners become indistinguishable and phase difference is lost. The triplet channel is symmetric. Partners remain distinguishable, preserving their directional phase relationship. To build an accurate topological model of the periodic table, we must map the first twist bifurcation properly. That requires activating this latent Spinor channel directly within the Z equals 2 geometry. Reducing a paired system exclusively to scalar arithmetic strips away the precise directional relationship between the coupled entities. To model how phase relationships actively maintain themselves, establishing a multi-component coherence field is mandatory. This branching theory is backed by physical precedent. We can observe both the scalar and Spinor channels at the macroscopic level in superfluid helium. When helium-4 atoms cool to near absolute zero, they condense through bosonic pairing. This is the exact physical manifestation of the theoretically predicted singlet channel. The entire superfluid state of helium-4 is governed by a single complex scalar order parameter. Because of this scalar restriction, any vortices that form in the fluid carry purely integer topological charges. Contrast this with helium-3, where atoms pair via fermionic coupling, providing the physical blueprint for the complex triplet channel. Helium-3 requires a 3x3 complex matrix order parameter. This multi-component spinor topology creates symmetry-distinct phases, half-integer vortices, and Majorana-like zero modes within the cores. Helium-4 and helium-3 are radically different topological phases, emerging from the identical Z equals 2 element. Any valid coherence theory mapping this element must natively encode both the scalar and spinor pathways. Mapping the triplet channel requires an update to our analytical framework. We have to utilize non-commutative matrix algebra. We calculate the new matrix-valued spinor coherence index by summing the Pauli matrices, each multiplied by its specific coupling function. The first coupling function, G1, governs symmetric phase exchange. It measures the phase strain difference between partners, modulated by the coherent memory they jointly retain. The second function, G2, drives helical phase circulation. It captures the memory asymmetry between the partners, modulated by their combined phase sum. The final coupling function, G3, measures fermionic coupling. It calculates the total system distinguishability by multiplying both the phase and memory differences. This creates a strict activation threshold. If the two recursion partners are mathematically identical, sharing the exact same phase and memory, all three coupling functions collapse to 0. The Spinor state neutralizes. The triplet channel exclusively triggers when there is structural asymmetry and a distinct phase history between the coupled parameters. Non-commutative algebra ensures that the exact ordering of operations is strictly preserved. This provides the ODTBT framework the mathematical capacity to map directional flow instead of merely aggregating static energy. This brings us back to a lingering problem from the ODTBT-10 series. We need to evaluate why previous models routinely failed to trigger targeted structural coupling outside of the Lorentz geometry, resulting almost entirely in effective system damping. The problem stems from the system probe. All 10 series testing relied on a Gaussian coherence kernel to interact with the target geometries. This graph compares the Gaussian coherence kernel from the 10 series data against the standard Maxwell-Boltzmann distribution used in thermal physics. The structural curves are mathematically identical. Because of this identical curve, the 10 series probe effectively distributed its energy across the entire thermal bulk of the attractor space. We can see the result in the lower panels. This broad, untargeted energy distribution yielded extremely low discrimination efficiency, leading directly to the effective damping classifications we recorded. We see the exact same thermodynamic constraint in plasma physics. A Maxwellian energy distribution leaves the vast majority of particles below the optimal fusion cross-section. It is the core inefficiency of conventional tokamak reactors. The experimental solution is to abandon the broad thermal distribution entirely in favor of a targeted, non-Maxwellian monoenergetic drive. This single-frequency drive is modeled by a pure delta function. It concentrates all available energy precisely at the system's resonant geometry. This mirrors colliding beam fusion, where all interactive energy is strictly confined to the optimal reaction cross-section. Broad-spectrum stochastic noise can only dampen a complex system. Triggering specific topological recursion requires highly concentrated resonant phase targeting. We can translate the theoretical Z equals 2 mathematical pairing directly into a testable, macroscopic format using a square Chladni cymatics plate. This chart diagrams degenerate mode pairs, modes sharing the same resonant frequency but with spatial patterns rotated 90 degrees. Their symmetric superposition generates the singlet analog, psi+, producing four-fold radial symmetry. Their antisymmetric subtraction generates the triplet analog, psi-, yielding two-fold directional geometry. Under standard, ungated driving conditions, environmental imperfections cause the plate to randomly alternate between these two states without any specific preference. Systematically controlling which of these two patterns emerges provides the physical proof of quantum Scalar-Spinor branching. The 20 series Phase 2 experimental protocols are designed strictly to isolate and test the difference between Maxwellian damping and targeted coherence gating. Protocol M represents the Maxwellian limit. We apply broad-spectrum, band-limited noise to degenerate plate resonance. Our predictions. Protocol M expects zero selection bias, with data hovering at 0. Protocol S applies symmetric modulation, predicting positive bias toward the four-fold singlet pattern. Protocol T applies asymmetric modulation, predicting severe bias toward the two-fold triplet pattern, confirming active spinor channel activation. The ultimate analytical discriminator is the bias ratio. The measurement recorded for the non-Maxwellian protocols must mathematically and significantly exceed the bias of the Maxwellian noise drive. If monoenergetic driving dictates mode selection while thermal noise fails, the reality of the Maxwellian partition and Z equals 2 spinor mechanics is undeniably verified.